After developing the nuclear model, Rutherford set about to test several of the behaviors. One of those behaviors is that one nuclei could be transformed into another. In order to test this, Rutherford directed alpha particles towards a sample of nitrogen. Nitrogen, as we know, has 7 protons and 7 neutrons. And in analyzing the results, he found that some of the nuclei had 8 protons and 9 neutrons. And this interaction would have left over 1 proton. And so what we had observed was the transmutation of nitrogen into another element, oxygen. And this is often regarded as the first observed nuclear transmutation. Contemporaries of Rutherford, Walton, and Cockcroft accelerated protons and directed them towards a lithium atom, lithium with 3 protons and 4 neutrons. The end result of this interaction was the formation of 2 alpha particles. Since 2 identical particles was formed, this is often understood to be the splitting of the atom, and led to further study. In 1935, Enrico Fermi took a sample of uranium and bombarded it with neutrons. After firing many neutrons at the uranium, he looked at the initial sample and noticed that there were some changes. Fermi concluded that there were heavier elements formed as a result of the neutron bombardment. He believed that he had formed elements 93 and 94, which were heavier than uranium at 92. Notably, Ida Noddack suggested that perhaps nuclei had split, making lighter elements. This led to the work of Hahn, Meitner, and Strassman. Again, they started with a sample of uranium and bombarded it with neutrons. When Hahn looked at the initial sample of uranium, he was surprised to find that there were some barium nuclei present, and there's no known transmutation that would take uranium to barium. He sent his results to Meitner, who had fled Nazi Germany, and she suspected that what had happened was a splitting of the nucleus. And in 1939, Meitner and her cousin Frisch explained this result. Essentially, what Meitner believed was that we started with uranium, 92 protons, 143 neutrons, and 1 neutron was shot toward the nucleus. This neutron was absorbed and it created an unstable nucleus, one that couldn't hold itself together, 92 protons, 144 neutrons. Because of the energy, it would start to pull itself apart. This still had 92 protons and 144 neutrons, but it would then separate into 2 distinct nuclei. And depending on the situation, these nuclei could be different, but one of the possibilities is that we would end up with barium with 56 protons and krypton with 36 protons. And depending on the isotopes that were formed, it could be possible that there'd be 3 leftover neutrons. And so in this reaction, we form barium-141, krypton-92, and 3 leftover neutrons. As with fusion, what we would suspect is that the total mass of the left-hand side and the total mass of the right-hand side would be the same. And so we add it all up. In this case, we have uranium-235 and 1 neutron on the left-hand side. We have barium-141, krypton-92, and 3 neutrons on the right-hand side. And then we look at the total mass, and we find that the mass of the left-hand side is greater than the mass of the right-hand side. Once again, we go back to Einstein's mass-energy equivalence, E is equal to mc squared. And in this case, we should release for every 1 nuclear fission, 170 mega-electron volts of energy. This, however, is not the only way the uranium nucleus can break up. So again, we have uranium-235, we shoot a neutron toward it. Again, we get the unstable uranium-236 pulling itself apart. And another possibility is that again we form barium and we form krypton, but in this case we have different isotopes. So in this case we're going to form barium-144 and krypton-90. And when we look at what's going on here, that would leave us with 2 leftover neutrons. And once again, E is equal to mc squared tells us in this case there's approximately 200 mega electron volts of energy released. While it's impossible to predict what's going to happen in any one reaction, we can look at the percentages of fissile products based on atomic number. So for uranium-235, the curve looks something like this. And the two that we've been talking about are here. And so we have krypton and we have barium. But as long as the two atomic numbers add up to 92, then we can have anything on this curve. The production of these videos has been generously supported by the Nova Scotia Teachers Union through the Program Development Assistance Fund.